So today, so later in the week I'll be talking about a general picture of combining bootstrap with gravity and understanding gravity from quantum field theory. Today is sort of a standalone talk on bounds on energy and transport. The main thing I want to discuss is number 4 on here. Actually, I don't know if on the video if you can really read. I'll try to write big, but the main thing I want to discuss here is number 4, which is constraints on transport from the ANEC. So the ANEC is a constraint on energy density in quantum field theory. And in the short story here is that in QFT, energy density, local energy density can be arbitrarily negative. That's a theorem. There's no such thing as bounding the local energy density. Total energy has to be positive. And there are semi-local positive quantities, including the ANEC, which is the integral over a null ray of null-null components of the stress energy tensor. So this is a constraint related to causality that goes back a long ways in the GR literature and recently has been understood from quantum field theory, and places constraints on coupling, is known to place constraints on coupling constants in CFTs and in gravity. What I want to discuss in this talk is a new application to relativistic hydrodynamics.
Is this the condition needed to prove the second law of thermodynamics in gravity? Is this what's needed to include with relativity?
No, I believe not. When I first started working on the ANEC, I thought maybe the answer was yes, and I was hoping to make that precise. Now I believe that that's probably not true. I think that there's an underlying stronger positivity condition that would give both the second law as a consequence and the ANEC as a consequence. I have some guesses for what that is, but maybe we can discuss it later. Okay, so I want to derive constraints on transport, and here's the plan for the talk today. I'm going to start just by there's a long history of deriving and trying to derive constraints on transport, and I'll start sort of by discussing that the status of that, starting with the famous bound on eta over S of Kovtun, Sun, and Starinets. I'll briefly just summarize the status of that. Then I'll describe these two constraints. The first one is a very simple one, just coming from the causality of the causal propagation of hydrodynamic modes. So this places an upper constraint on diffusivities, and then I'll go on to this more elaborate bound coming from the ANEC. The two ingredients that go into that are the ANEC and a random matrix ansatz for finite temperature systems called the eigenstate thermalization hypothesis. So I'll explain what those ingredients are, and mostly I'll just be sort of trying to tell you how to put those various ingredients together in order to try to say something about transport. The bounds that I'll end up with, will potentially be bounds on real-world things like the quark-gluon plasma, but the bound is, as we'll see, is not very strong and sort of sits at the edge of the regime of the QGP where you might hope to apply it. So it's not really clear what the status is as far as actually getting the constraint on that system. Okay, so let me start with just some general comments about hydrodynamics. So we're considering a quantum field theory at finite temperature. And we'll be talking about correlation functions in that theory. The fact that it's at finite temperature means that the theory is effectively gapped in that correlations fall off exponentially with distance or with time, with the exception of a few hydrodynamic modes. This is basically the definition of hydrodynamics. You take a system at finite temperature, which typically, although maybe not always, will be gapped at low energies. And So the statement is that correlation functions, like a 2-point function, are suppressed in time by the thermalization time scale, suppressed in space by the thermalization length, plus hydrodynamic modes. So the only long-lived modes are the ones that are connected to conserved quantities. The cutoff, so the hydrodynamics is an effective field theory at low energies whose cutoff is this thermalization time, tau, or the thermalization length. In this talk, I'm not going to make a distinction between the thermalization length and the thermalization time. I'm going to assume that these are the same, but this is not always true. And to get for the more general case, we'd have to worry about that. But essentially, I'm talking about whatever is the largest definition of cutoff you can come up with. Okay, so what is hydrodynamics? Well, if we look at a 2-point function, the 2-point function in particular that I'm going to be interested in is the T++ retarded correlator at finite temperature. The reason you can guess the reason that we're looking at these all null components is because eventually we're going to want to talk about the average null energy condition, which is a statement about the null components. But if you look at a correlator like this, and this is true for any of the components, not just this one, but if you look at this correlator on the complex omega plane, then the correlator will typically have some poles or maybe cuts in the lower half plane that stay away from the origin. And then there'll be some hydrodynamic poles near the origin. So these are, in particular, there'll be a sound pole, which is omega is CSK. This is linear, so this is the sound pole. And there will be a diffusion pole on the negative imaginary axis. Omega, with dispersion omega, is minus I d k squared. And I've written this diffusion constant as d sub eta because if we're talking about these components of the stress tensor, then this is the diffusivity for momentum, which is related to the shear diffusion. So
and the sound pole is also a little bit under the axis.
Yeah, that's true. Yeah. Yeah. Right. So as we take k to be small, then there'll be some non-hydrodynamic stuff here in the lower plane, which will not scale to 0 as we send k to 0. That, for our purposes, that's the UV. That's properties of the UV theory. That'll depend on the details of where your hydrodynamics is coming from. And there will be these modes near the origin. And well, there are many ways to define what hydrodynamic means, but for my purposes, this is the theory of hydrodynamics. It's the theory of these poles near the origin in stress-stress correlations like this.
And this gap is like order this cutoff, you said?
Yeah. So so this cutoff, like this thing here, would be at minus I lambda. So the distance to the UV stuff is defines for you the cutoff of the effective theory.
And dn is typically 1 over lambda, of order 1.
Dn does not need to be of order 1 over lambda. Why do you say that? I think it's true like in holographic theory.
In a conformal field theory, with no small coupling, it would have to be.
Yes. Okay. Yeah. That's, I mean, to some extent, that's part of the motivation of this talk. In holographic theories, it's just sort of set by dimensional analysis. And there's this whole discussion in condensed matter of the so-called Planckian bound, which is just the statement that diffusion constants like this are set by dimensional analysis with the temperature, or that that's or that bounds the diffusion constants. And that's sort of part of the idea here is to ask, well, it seems like it should be set by dimensional analysis, but do we really know if it's set by dimensional analysis? Could it be, yes, it should be set by the temperature, but could there be a dimensionless factor of 10 to the 10 sitting there, or 10 to the minus 10? So that's part of the goal, is to understand whether you can have tunings like that in the low energy theory.
But let me understand that. In weakly coupled n equals 4 angles, what is the relationship between these two? These two, do you know?
Between, what is D?
Delta and dn. There's a coupling constant dependence in each of them. Is it the same coupling constant dependence? Do you know?
Let's see. No, I don't know.
I would guess it's the same, because both are coming from collisions in some way, but I'm not sure. Maybe there's a square.
Okay. Yeah, I'm not sure.
Yeah.
I think maybe they differ by 1 power of g.
It could be.
One is g, and the other has has a g squared.
Yeah.
Yeah. Okay, so this hydrodynamic theory, you can completely fix up to the transport coefficients. The way to do this is by solving the conservation equation for the stress tensor, and by solving this equation in the hydrodynamic expansion, you can, in a relativistic theory, you can completely fix the hydrodynamic TT correlation function for all the components of the stress tensor. So this is some known function, which I won't write down because it's pretty complicated looking, but this is a relatively simple known function that depends on the speed of sound cs, the shear viscosity eta, the bulk viscosity zeta, and s times t, where little s is the entropy density. In position space, you can Fourier transform this to find the position space correlation function. And in particular, I'll just write the contribution to this from the diffusion mode. The contribution from the diffusion mode is just a Fourier transform of basically 1 over omega plus I dk squared, which is grad squared exponential minus x squared over 4 d eta t. So this is the this e to the minus x squared over 4 dt is the famous diffusion law that is basically parabolic. The diffusion constant that shows up in that exponential is eta over st. Okay, so I'll sort of be phrasing things in terms of diffusivity d, but we're also talking about the ratio eta over s. Often these bounds are phrased in terms of eta over s, but it's a bit easier for my purposes to phrase them in terms of the diffusion constant. So these diffusion constants are extremely difficult to calculate. There are very few cases where you can do it. You could do it in kinetic theory, in a weakly coupled gas, but beyond that, there's essentially no methods to calculate diffusivities in strongly interacting systems. There's holography, which works if your theory happens to be holographic. And somebody correct me if I'm wrong here, but I don't know of any other method to do this at strong coupling, to actually get a number. So there are Monte Carlo methods and DMRG-based methods that people have tried to adapt to this sort of calculation. But my understanding is that so far they can't really reach the transport regime, that they can't calculate transport coefficients even numerically, essentially just because of the sign problem. You can't avoid the sign problem when you go to real time, and transport is a long time, real time phenomena, and there's just no way to escape this problem, so the numerical methods don't work. So this is a great sort of target for high energy theorists or anyone thinking about quantum field theory or people thinking about bootstrap in quantum field theory. This is a great target, I think, for something to calculate or something to constrain. Now,
why only a strong coupling? Weak coupling, I can just use Feynman diagram to do it.
Well, in weak coupling, I think you can calculate things like this in kinetic theory. It'll be related to the mean free path and some small coupling constant.
All these sign problems do not appear in the weak coupling.
Well, for a sign problem, I was referring to like Monte Carlo methods. I think in weak coupling, I think you can do this analytically in kinetic theory in terms of the mean free path. So it's really only when you get to systems where you don't have a quasi-particle, essentially free quasi-particle description where there's a problem. And there, the closest, I think the closest you can get to being able to calculate it is Monte Carlo, but you really can't get a reliable number yet even out of Monte Carlo. So Kovtun, Sun, and Starnetz famously calculated this diffusion constant holographically for Einstein gravity, and they found uh, 1 over 4 pi, and they conjectured that the ratio 8 over s was bounded below by 1 over 4 pi for all quantum systems. This was based on based on examples partly, but also on some intuition about the uncertainty principle. And I would say the status of the KSS conjecture is still, after many years, basically inconclusive. Now, the original conjecture is not true. There are counterexamples to the original conjecture. So that's one reason that it's so hard to prove. But there does seem to be some truth to it. I mean, it's not just that it's completely wrong or easy to violate. There does seem to be some truth to it, and it could be that you can modify it and get something that's exactly true. A more recent version of this conjecture, due to Hartman and Blake and others, is that diffusion constants are bounded below by, well, this would be the KSS bound, but what they added to it was dependence on the butterfly velocity. So if the butterfly velocity, which describes how chaos propagates in the system, is different from the speed of light, then it gives you an extra dimensionless number that you can include, and there's quite a bit of there are quite a few examples, many of them holographic, for this version of the bound actually being true. There are some claimed counterexamples even to this one, but then there are counterclaims to the counterexamples. Okay, so I would say that this is still sort of an active area and still open. There does seem to be some kind of set of bounds like this, but it's not exactly clear what they are. Okay, so the goal of, so I'm not going to prove the KSS bound either, but the goal of what I want to discuss is to talk about the extent to which we can prove some bounds from first principles in QFT on these quantities. So we want inequalities on diffusion constants like d eta and the cutoff of hydrodynamics, and to understand whether they're general constraints on the transport coefficients.
So the violations of the case is bound coming from the higher derivative terms in gravity. They can be understood as this additional factor VB by C whole square.
Well, no. Okay, so there's at least two kinds of violations that I'm aware of. The first were small violations which came from higher curvature corrections. Those violations, I would sort of say, still fit into the original KSS because you could fix them by putting a minus epsilon here. So that's a very mild violation. But then there was a different type of violation coming from anisotropic systems, which Sachin and other people studied. And here you could make a parametric violation of the KSS bound. So it's those parametric violations of the KSS bound, where this VB over C is what saves you and makes the bound true again. So there were, I guess, not just anisotropic, there were anisotropic as well as these more exotic scalings like hyperscaling violating different dynamical exponents. And this one is correct in all of those cases.
For conformal field theories, Lorentz invariant conformal field theories, relativistic conformal field theories, you would say that first bound, some small modification of the first bound is still viable.
Is still in play. With conformal in conformal where? You mean in the UV? Because you can have even if it's conformal in the deep UV, you can have sort of emergent anisotropic scaling regime. You can have regimes partway to the infrared that have like Lifshitz geometries or whatever. So
A theory with a conformally invariant vacuum, and then just temperature on top of that.
I think you can construct these type of geometries in theories that are conformal in the UV.
Without an operator information. Just turning on a temperature at a theory that's conformal.
Yeah,
That's
I guess
conformal.
you would need there to be some instability for some other field to turn on. I thought this was. I'm not sure if that's possible. I thought that was possible, but I'm not sure.
Is there anything known about the lambda dependence of this Pythagoras in the Helicospores parameter?
The 't Hooft lambda?
Yeah. I
Um,
mean, it's a bit difficult to imagine that for any value of lambda, this some version of the bound with epsilon modification continues to hold.
well, certainly in the weakly coupled limit, 8 over s goes to infinity. So I think the expectation is that this is infinity at weak coupling, and just it goes monotonically. But I don't think we know the intermediate behavior. Okay. Other questions? Okay, so let me state the two bounds that I want to tell you about. There are two different bounds coming from two different arguments. The first one is causality of this TT two-point function. So this is a relativistic theory, and TT has a certain analytic structure dictated on it by relativistic invariance.
I have a request actually, Tom.
Yes.
Can you write a bit below, because I cannot see actually when you're writing on the top part.
Okay. Yeah.
Unfortunately, because of the bandwidth or something. So a little bit below will be fine, if you don't mind.
Is that better now with the lights, or
Put it up.
Maybe. It's better. It's better. But yeah. No, I think still it's difficult, but never mind. I think it's better now. It's better. It's better.
Okay, I'll put a line or something so I don't go above. Okay, so this is going to. I already went above. Okay, so this is going to put a bound. One way of stating this bound is it tells you that there cannot be a parametric separation between the cutoff and the length scale, or sorry, the energy scale set by the diffusion constant. Okay, so this is the way to think about this is that you have some low energy theory with a coupling constant in it with dimensions of energy. That's this diffusion constant. And what this says is that you must have new physics at the scale set by that coupling constant. Now, this is kind of what we expect from dimensional analysis and effective field theory. We expect that if we have length scale, that if we have length scales set in the infrared theory, that's the length scales of new physics. But there's nothing in ordinary effective field theory that tells us that there has to be, usually, in general, there's nothing that tells us that there really has to be something at that scale. This is not a strong coupling scale of the low energy theory. And so this is a non-trivial bound that tells you that actually in this case, there really does have to be new physics there. The second constraint and the first one I'm gonna explain only very briefly. This is something that actually has been, well, I'll come to it in a minute, but it's fairly simple. The second one comes, as I mentioned at the beginning, from the ANEC, the average null energy condition, combined with the ETH, the eigenstate thermalization hypothesis, and this also can be phrased as a bound on the cutoff of the effective theory. In this case, it's complicated enough that I can't really write the bound in closed form, but it takes the form of an upper bound set by the dimensions set by the temperature times some dimensionless function of 8 over of all the transport quantities, 8 over s, zeta over s, speed of sound, and the entropy. And I will give some examples of limits where we can make sense of this function. Okay, so one caveat that I'll just mention here is that the causality and the ANEC are themselves related in a deep way in quantum field theory. The ANEC is really a part of what you mean by causality in a quantum field theory. But these are two different bounds. And the relationship between ANEC and causality is a different thing. This here is causality of just propagating hydrodynamic modes in a thermal background. The connection between the ANEC and causality is more indirect. Okay, so it's a different type of causality that's responsible for the ANEC.
I get confused about something probably stupid. You motivated the first bound by saying that in effective field theory, you would expect that terms in the derivative expansion cannot become too large compared to the cutoff. I'm getting confused. The inequality looks like it's the other way to me. So
this is the energy cutoff.
Good. So suppose I think of the expansion of hydrodynamics.
Yeah.
And then there's the first term, which is goes beyond the perfect fluid, which is proportional to the viscosity.
Yeah.
If you want to say that that term cannot be at a fixed high energy cutoff, that term cannot be too large. That would tell you that the viscosity has to be less than something, whereas the actual bounds tell you the viscosity has to be greater than something.
Yeah.
It's not a very important question, but just to get the way of thinking.
I think it's sort of a normalization. I think it's sort of a normalization issue. You know, we could move around where the etas appear. I mean, you're right. You're right. It appears on the top in the equations of motion. What? Oh, yeah. Wait. Yeah, it is eta less than something.
Wait, up there, eta would appear in the numerator and the exponent, right?
Well, this is d inverse is greater than something, so that's eta less than something.
Oh, how does d eta?
D is eta over s.
Ah, so it's eta is less than something. So that's strange because we know the bound.
Yes. This goes the opposite way of KSS.
Ah.
That's right.
Ah.
Yeah. You know, we were originally motivated by KSS, and we were trying to use the chaos bound and the ANEC and these kinds of ingredients, thinking that maybe we could derive KSS. But that's not what happened. What happened is we kept trying to derive it and getting different bounds instead.
But opposite bounds.
Opposite bound. Well, this one is opposite. This one is a little more complicated. I'll draw a plot that yeah.
Okay.
Yeah. I mean, it's not opposite because that's not 1 over 4 pi.
I understand.
But it's in the opposite direction. Yeah. Okay. So both of these bounds say that hydro alone with viscosity has some problems if you take it too seriously, and that you need some physics in the UV to fix that. This is along the same lines of things that I'll talk about later this week involving the Gauss-Bonnet term in a theory of gravity. So there, you add the Gauss-Bonnet term, and you find that when you add the Gauss-Bonnet term, the theory has problems that you need to fix by adding new physics, which in that case are strings or something similar to strings.
Sorry, and just going back to what you said at the beginning, this you believe is parametrically obeyed at weak coupling.
Yeah, these are obeyed at weak coupling. The trivially obeyed. This one is trivial. Yes.
Parametrically at coupling.
Yes. Yes.
No, but didn't you say that at weak coupling this goes to infinity?
Or both.
8 over s.
Lambda also?
Lambda also, because the decay is because of collisions. There's no decay with them.
Yeah. Yeah. So if I take these, I'm going to draw a plot. Before I'm going to discuss the derivation of these constraints, but first let me draw this plot. So on the horizontal axis, I have the diffusion scale d eta inverse. On the vertical is the new physics. So this is lambda. And what these constraints together tell you is that, first of all, there's a linear, so there's as d eta inverse increases, there's this linear bound on lambda. So that bound looks like this. This other bound, I haven't told you the function, but it has very weak dependence on 8 over s. So if you plot this, if you take all the other transport coefficients and set them to reasonable sort of order 1 things, and then you plot this just as a function of 8 over s, then it's very flat. It's a very flat function. So it looks something like this. So what these two bounds together tell you is that there's this is the allowed region is under here. So what these two bounds tell you together is that you sort of carve out this perimeter space in the plane of the coupling constant of the low energy theory versus the cutoff where the new physics has to come in. So this is the allowed region. It's tempting to try to put theories that we know of onto this plot and see where they fit in. The problem with this is that the bounds that I'm discussing here are really parametric bounds. They're not strict inequalities with known order 1 coefficients. When I say that lambda is bounded by d eta inverse, what I really mean is that lambda cannot be parametrically above d eta inverse. So these are fuzzy bounds. And if you try to put, for example, the quark gluon plasma on this plot, then it basically lives there, sort of near the intersection of these two bounds. But the error bars on these things are large. It's not clear whether there's some sense, one thing we wanted to understand was whether there's some sense in which something like the QGP is pushing up against the edges of this allowed parameter space. It's very strongly interacting. It has very low 8 over s. We might think that it's sort of trying to push against these constraints. That does appear to be true, but not really but it's all comes down to these order 1 numbers that we don't know, so we can't say it with much confidence.
Suppose you take the finite temperature theory, put it in a circle, so you get an effective 3D, just in Euclidean space.
Yeah.
Would the mass gap of that Euclidean theory give you a measure of your lambda?
Yes. Yeah.
So, can you explain once this? Lambda was a gap from the hydrodynamic mode to the next quasi-normal modes.
Yes.
And that you're saying those are, and I can study hydrodynamics irrespective of those. What is my new physics at lambda? What does it mean?
That means whatever's UV completing hydrodynamics needs to show up at lambda.
And it does not, and it affects the hydrodynamics that we are discussing. Like. Well,
yeah. So the KSS bound is just a statement about hydrodynamics. It
Right.
only involves 8 over s in it, and but that's not what we found by our methods. We didn't find any constraint on just hydrodynamics. What we found instead are these bounds that tell you about the relationship between hydrodynamics and the scales of the UV theory. So we don't, in the end, have any constraint purely on hydrodynamics itself. The constraints are on hydrodynamics together with the cutoff. So it's a little more, it really is more like the story with the Gauss-Bonnet coupling. It's not that. So for example, if I tell you that the gravitational theory is Einstein plus Gauss-Bonnet, then the Gauss-Bonnet coupling could be anything. Like there's no constraint on that theory. But once you know that the Gauss-Bonnet coupling has a certain value, then you also know that there are strings at that scale. It's a little like that. It's that the parameters of the low energy theory can still apparently be anything as far as we can tell. But once I tell you those parameters, I've also told you something about what the UV degrees of freedom are that are making up that low energy theory.
So the Gauss-Bonnet gravity also you should be able to plot on this plane.
Yeah. So we could put gravity on here, and let's see. I think gravity goes.
Isn't it roughly a 45-degree line?
What?
Isn't lambda just the two scales more or less equal for Einstein gravity?
Well, for Einstein gravity, okay, so this, when I drew this upper curve, I said I was just setting everything to reasonable sort of order 1 things. Einstein gravity has this extra n squared in it. So what happens is Einstein gravity also sits here on the plot, but for a large n theory, this exclusion line moves way up here, and it's not near that constraint. So it sits here, but the line is up here.
Oh, so it's like, as you said, the lambda would be order temperature,
Yeah.
but it has n squared times.
Yeah, the constraint on, yeah, exactly. The constraint has an n squared, so it's trivial. Okay, so the first one I'm just gonna tell you very briefly where that comes from, and then we'll go into the second one. The first one really just comes from. Yes.
Yeah. So doesn't the n square cancel in the d eta?
Sorry?
Doesn't n square cancel in d eta when you go into the diffusion constant? Or
Yeah. So in holographic theory, 8 over s is an order 1 number, but what we'll see is that the second bound has a n squared on the right-hand side of it, and so is trivial in a large n theory, where the left-hand side has no n squared.
Okay. Okay.
Okay, so the causality bound really just comes from plotting this function.
Sorry, but the first bound was non-trivial even in large n.
That's correct. Yeah, and in fact, the first bound, like if you put this, if you look at this bound in gravity, it gives you a constraint on the frequency of the first quasi-normal mode compared to 8 over s, which you could check is true, including even the order 1 numbers here, and it's true in a not obvious way. Okay, so it does give you sort of a prediction for how the quasi-normal modes have to behave compared to 8 over s. And there are systems where you can tune those numbers, and you can check that things change appropriately.
So when you have large n, then even though this flat line goes to infinity, the QGP point remains where you have plotted it. Is that right or not?
Yeah, this QGP point is just the experimental values of transport and the cutoff. This is the thermalization. For QGP, by cutoff, I mean the equilibration time inverse, which is something that's basically measured. Okay, so the causality bound is really simple to understand where this comes from just by plotting what it looks like when something diffuses. Okay, so when something diffuses, it essentially travels on a parabola, right? Because this exponential here is a parabolic relationship between x and t. So the sort of diffusion front looks like a parabola. So this is what diffusion. Like if I were to try to send a signal using a diffusive process, this is the best I could do. Now, at late times, it's very hard to send signals with diffusion, but at early times, it's very easy to send signals with diffusion. Diffusion goes too fast at early times. So the light cone in a relativistic theory is linear at early times. Diffusion starts out parabolic, and that's where this constraint comes from. Okay,
so the constraint is simply that where you trust this analysis, it should not violate.
Exactly. So if you just look at this plot, it doesn't make any sense in a relativistic theory, and the resolution of that has to be that the cutoff scale of your effective field theory, where you can trust the plot, had better be big enough to make this. So really, there's some fuzziness in this diffusion propagation. because there's some cutoff of the low energy theory. And where that bound comes from is requiring that the fuzziness or the cutoff, where you really don't trust the fact that you've sent a signal faster than light, you require that fuzziness to be big enough that things could actually travel inside the light cone. So if you try to parametrically violate that, then you'll be able to send signals faster than light. So it's been understood for a very long time that first order hydrodynamics is acausal, that you can send signals arbitrarily fast, and often that's fixed by going to second order hydrodynamics, and then you get constraints on the second order transport coefficients. But a more general way of stating it, I think, is just to understand this in terms of the cutoff of the low energy theory. So that's where that first one comes from.
So,
And
so the fuzziness should be such that it should be inside the light cone, you mean, in this graph?
yeah, that's right. Yeah. Essentially, the fuzziness should be big enough that it never really violates that light cone.
And can you just say once, how exactly is, so in computation, you're saying the error would be of the order of lambda, is it? What do you mean by the fuzziness?
The fuzziness on this picture is essentially lambda inverse.
That you can trust.
Yeah, yeah.
So in terms of the pole for the diffusion, which looks like omega equal to minus I by d is k square.
Yeah.
If you go to second order, it picks up a linear term. Is that what you were saying?
Let's see. Not exactly. Okay, so generally, that's one way to do it. If you include a second order transport coefficient and you make it big enough, then that will make that'll make the equation causal. But that isn't the only way to make this work. You can also have it so you have to have sort of a very special system if you want to be able to balance the second order effects versus the first order effects. Right? Usually, if the second order effects start competing with the first order effects, it really means that all the higher effects are going to come in and your whole analysis is breaking down. So there is some limit you can work in where you trust that second order analysis. But more generally, I think we just have to phrase it as a breakdown of the low energy theory, as opposed to a statement about the second order contributions.
I was just thinking of the function. If some function starts out as k square and you keep adding all kinds of stuff,
Uh-huh.
then, how can it effectively become linear in k?
Ah. Yeah, it's not that let's see. I don't think it's that it really has to become linear. It's not that it's not that diffusion is really going to propagate on the light cone. It's just that we want it to stay inside the light cone. So I don't think it's actually going to become linear. Yeah. Okay.
Just to make sure I understand. So when for the KSS case, deta is like 1/4 pi. In that case, it's always inside the light cone. In the KSS case, because there is lambda, as you said, like lambda is infinity, or lambda inverse is just 0.
Yeah, it's always, let's see. Right. I mean, you have to say what lambda is. It's the string scale or something. But you can make lambda very big, and then there's no problem.
Well, wait, lambda is the temperature scale, right?
Sorry. Let's see.
And n equals for animals.
Right. That's right. Lambda is set by temperature.
So
That's
KSS
right.
doesn't say anything about whether it's violated or not. Right? Parametrically, it's not going to be violated because it will be approximately the same.
Yeah, they're basically, the two sides are basically the same in gravity. It's basically saturated.
Yeah.
Yeah.
You're saying the fuzzinesses of order lambda inverse because to this correlation function there is corrections that you get which are of order lambda inverse. That's the fuzziness.
Well, lambda, this is the thing that shows up in the exponent. So decays are correlators are exponentially decaying, and this is setting the scale of that exponential decay. That's the definition of lambda.
One way of saying this is nothing in this solution should be trusted unless x and t are both large compared to lambda.
Yeah.
So where x and t, if this violation will happen,
No, but this is coming because
there are higher order corrections.
Yeah.
Right.
Sorry, a stupid question. If we look at gravity as a function of dimension, do you know if do you take dimension large with something interesting happen?
I don't know. That's a good question. I don't know. There could be some D's. There could be D's entering the constraint. I'm not sure. I guess there'd be some D's entering these Fourier transforms, which we would have considered OR1 numbers when we did it, but yeah, I don't know what'll happen.
Maybe you could rule out the existence of semi-classical. No, probably. Yeah, causality is probably true. Yeah, okay.
Okay, so as I mentioned at the beginning, the ANEC is this statement about the integral of t plus plus over a null ray being positive. And this is not really an obvious statement about quantum field theory by any means. It goes back to the general relativity community where they basically guessed this because it was the best thing they could come up with that was good enough to prove lots of theorems in GR, like singularity theorems and wormhole theorems about traversable wormholes and causality. This was the minimal assumption they could come up with that wasn't just clearly violated in quantum field theory. And they did calculations in free theory to check that this was true. They couldn't come up with any counterexamples. You can prove it in various free cases. More recently, it's been understood as a general property even of interacting quantum field theory. There's a derivation using information theory, and there's a separate derivation using correlation functions. But for our purposes today, we're just going to use this as an input. It's some fact, non-trivial fact about relativistic quantum field theory, and we want to see if we can say anything about transport.
So derivation is in the CFT or in the QFT?
Well, the quantum information derivation doesn't care if it's a QFT or a CFT. It does have some potential assumptions about what it means to split a Hilbert space in two and exactly how you're supposed to regulate relative entropy in quantum field theory. The correlation function derivation of the ANEC is a CFT derivation, but also applies to CFTs deformed by relevant operators. There's some extra assumption that goes in when you try to deform it with a relevant operator. But it's some assumption about there's some extra assumption that goes in essentially into the derivation where you have to assume that certain correlation functions factorize at late times. But with that assumption, it doesn't require conformal invariance.
So just one random comment. In the large D limit, there is a limit in which you can effectively send the higher quasi-normal modes up to infinity. while keeping an interesting nonlinear theory of the lower quasi-nominal modes, which includes viscosity, which includes some sort of viscosity.
Oh, right. Okay.
So I wonder how that interplays with this. It's always happening in a context in gravity. This is always happening in gravity in a context where gravity is manifestly causal.
Yeah.
So it must agree with it, but there may be something interesting to say.
Huh. Yeah. It could just be that there are D's coming into the Fourier transform and entering the two sides of that inequality.
Yeah.
I'm not sure.
Yeah.
So what does the ANEC do for you in quantum field theory? Well, there's a famous result of Hartman and Maldacena called the conformal collider bounds. And what they did is they studied the ANEC in states created by the insertion of the stress tensor. Okay, it has to be positive. When we say that this is a positive operator, we mean its expectation value is positive in any state. So in particular, it's positive in a state created by the stress tensor itself. And Hartman and Maldacena used this to derive constraints on the various coupling constants that show up in the TTT three-point function. In a CFT, there are 3 of these. Okay, so they found some inequalities on those couplings. More recently, there's been a study of interference effects, what they call interference in the conformal collider. So this is a result from a year or 2 ago of Cordova, Maldacena, and Turiachi, whose initials I also like. And what they did is they took a state that was a linear combination of a state that you get created by the stress tensor and a state that is created by some other operator, say a scalar operator O. Okay, so if you apply the ANEC in this linear combination state for all possible alpha and beta, then what you get is a matrix inequality. Which tells you that some matrix, I'm writing this sort of schematically, but it basically tells you that the matrix formed out of the various terms that you'll get here, that the matrix there has to be a positive semi-definite matrix. So this is positive semi-definite.
OTO is essentially the dimension of O, right?
That's right. Yeah. Yeah. If O is a scalar. Yeah.
Sorry, OTO. No. T with O is
Yeah, that's right.
Yeah.
Okay, so if you think about, so this tells you that all the eigenvalues of this matrix, well, both the eigenvalues of this matrix have to be positive. So what that means is that it constrains how big these off-diagonal terms can be in terms of the diagonals. Right? If you have a 2x2 matrix like this, then for it to be positive semi-definite, you're basically going to constrain something like this coefficient times that coefficient bounded by the product of the diagonal coefficients, right? I think the takeaway part, the important part that we're going to use here for hydrodynamics is the lesson that eigenvalue repulsion, in this case just for a 2x2 matrix, but eigenvalue repulsion makes the ANEC stronger than it naively appeared. You know, if we could have just studied these two states individually, and we would have gotten some positivity conditions. But by putting this into a matrix like this, we get a stronger constraint due to eigenvalue repulsion.
Wait, so does this condition, when you apply it, tell you that COTO has to be less than something bounded by the dimension of?
No, the other way, right? It's the product of these is less than the product of those.
Good. So COTT is less than dimension times some CTT.
Yeah, that's right.
So if you can't take dimension of the scalar to infinity and have it be produced also by collision of two gravitons. The CTTO is,
Well, unless they're, yeah, I guess you could scale these. No, if you make this infinity, then you can do whatever you want.
oh, I see, I got it, yeah.
Yeah,
Fine.
yeah. Okay, so why am I telling you this? Well, I'm basically going to apply this same interference logic now to hydrodynamics, and that's where the constraint comes from. Let me give you the intuitive picture. So in hydro, we can apply the same logic to the eigenstates that make up the canonical ensemble. So what I'm doing now is taking some system that's in some hydrodynamic state. The kind of state that I have in mind is a state like a localized ball of hot stuff. Okay, because I need these quantities to be finite. So I need to sort of put the system in a box, and I'm actually going to put in a 1 over L box here in order to make things finite. We need to be finite, but we need it to be acting according to the laws of hydrodynamics. So we're going to have some finite box of stuff or fireball of stuff, which is hot and acting in the hydro regime, and is just vacuum elsewhere.
For that to be positive, it had to be integrated to infinity?
That's right, yeah.
So you were working in the L goes to infinity limit.
No, the integral is to infinity, but the box is finite.
What is, oh, you mean it
By box, sorry, by box, I mean that you can either physically have a box like made out of cardboard, but you have to integrate through the walls of that box, or I can just talk about a state where the stuff is localized.
Or you could put it on a torus and let it just wind around?
The torus, I think, will get into trouble because I don't think the ANEC is true on a torus.
Ah.
Yeah, I don't think you can put it on a torus. You really have to have some finite extent of your hydrodynamic system and then do these integrals to infinity.
So the states are localized. Why is it necessary that the integration contour passes through the locus, or passes through that support? It could pass it also.
Oh, yeah, it could, but we're going to choose it to go right through the fireball.
If the fireball is localized, then why do you have to put the normalization 1 over L box like that? That L box is what in that case? Is that the...
This is the size of the fireball.
Fireball?
Yes. Yeah. No, we don't need that. But yeah, sorry, we don't need this here. I'm just putting it in to emphasize that the matrix elements that we're calculating will depend on the size of the box. Yeah. Okay. So now we're going to calculate the ANEC in the states, in the microstates of the fireball. Okay. So there's some fireball. There's some microstates that make up that ensemble that's responsible for the fireball. So there's some enormous matrix whose size is e to the s by e to the s. And this is the matrix so this is labeled by these microstates of the fireball. And in that matrix, we're going to calculate, or rather, we're going to calculate the matrix elements of the ANEC operator in those states. So let's first think about the diagonal pieces of this matrix. The diagonal pieces of this matrix are easy because well, if these were exact energy eigenstates, then this plus plus component of T would just be the energy density plus the pressure. For a large system, then there's, well, part of the eigenstate thermalization hypothesis states that actually this is true. This is actually true of essentially all of the states along the diagonal. It's not just an average property of the ensemble. It was actually individually true for the matrix elements along this diagonal. So the expectation.
I have a question.
Yeah.
Sorry, I have a question actually. So you said that the size of the matrix is exponential of the entropy times exponential of the entropy, right?
Yeah.
So, however, you are doing hydrodynamics, so there is a low energy projection. So why is the Hilbert space so big?
This is so this calculation is being done in the microscopic theory, not in the hydrodynamic effective theory.
But you said that the state I represents some some state which is like a hot fireball of a certain extent. So okay, this counting is something I'm not understanding actually. I understand that if you have the microstates, then you have e to ds, cross e to ds. But
yeah, so I'm choosing my states to be those microstates. So this is a state in the UV theory that's keeping track of where every single little particle is and all the microscopic details.
Okay. Fine. So these are the microstates of the ultraviolet theory, correct? Okay, got it.
Yes.
Got it.
Yes. Okay, so the diagonal part of this matrix is just set by thermodynamics and is the energy density plus the pressure. The off-diagonal part of this matrix will be related to the hydrodynamic fluctuations of the low energy theory. And I'll give an equation for this in a minute. But basically, the reason for that is because the TT 2-point, so hydrodynamics is a statement about the TT 2-point functions. And in the microscopic theory, you get the TT 2-point functions by squaring this matrix. Okay, so at least on average, we expect the off-diagonal elements to be controlling and related to the theory of hydrodynamics. So now, if we ask that this giant matrix be a positive matrix, since the ANEC is a positive operator, then
This is not a complete set of states that you're inside here, right? This is just some states that you pick. So in what sense squaring it would give you the TT2 function?
You're right that you really need to have a complete set of states to do that. But the contribution to the 2-point function will not come from some very far away energy eigenstates. It'll come from the same set of states. I'll write a more detailed formula in a minute. Maybe ask me then if it's still not clear. Okay, so essentially now we're going to use the same logic that showed up in the interference experiment. In the interference experiment, the logic was that positive semi-definiteness here bounds the says that the off-diagonal has to be less than diagonal. Same sort of thing here. So this is going to tell you that the thermodynamic equilibrium quantities bound the hydrodynamic transport quantities. So this was sort of the, so far I haven't assumed anything, I haven't assumed much, but in order to make this quantitative, we have to assume something. And what I'm going to assume is eigenstate thermalization. So eigenstate thermalization, or ETH, is the statement that local operators like T++ in high energy eigenstates with finite energy density have a diagonal piece given by the thermal expectation values and an off-diagonal piece which has two pieces. So the off-diagonal piece is a smooth function of the conserved quantities. So in this case, Pi and Pj are the momentum of those states. So it's a smooth function of the conserved quantities. And it's of order e to the minus s over 2. I'll come back in a minute to why it's e to the minus s over 2. And the second piece here is a random matrix of zero mean and unit variance. So eigenstate thermalization is an idea that goes back to Sredicki and Deutsch in the 90s. It really is not, at least to me, an obvious fact at all. I think that there really are, there's sort of two ways you can imagine quantum systems behaving according to the laws of thermodynamics. You might imagine that thermodynamics or hydrodynamics comes out as some averaging over the microstates of the quantum theory. I think that probably would have been my guess if I didn't know about ETH, is that eigenstates are not what you make in the lab. What you make in the lab are some very messy combination of eigenstates, and you can imagine some averaging of those messy combination of states leading to approximate hydrodynamic or thermodynamic behavior. But that's actually not what happens in chaotic quantum systems. This is known through examples and numerics. But what actually happens is this. It's that individual eigenstates in a chaotic system have themselves already sort of built into them the thermodynamics of the system. So individual eigenstates are already behaving hydrodynamically, or thermodynamically rather.
Are these high energy states? Excuse me. Are these high energy states that you're talking about?
Yes, they're high energy in the sense that they have to be high enough energy that they can be described by, that they are part of a thermodynamic ensemble. So, so this diagonal piece here is here to reproduce thermodynamics. The off-diagonal piece is here to reproduce hydrodynamics. Okay, so that's how it's determined. It's basically you take this ansatz and you ask for it to give the correct two-point functions. That's where this e to the minus s over 2 comes from. It's because the contribution, you'll have to square it, and you get an e to the s or an e to the minus s, and then you sum over e to the s states, and you want your two-point functions, your fluctuations, to be order 1, or well, not to have any e to the s's in them.
So earlier you introduced this lambda.
Yeah.
This ij scaling dimension has to be related to lambda or no such relation?
Lambda, big lambda?
Yeah.
These have to be, well, these have to be states in the theory below lambda. Although, I mean, that's kind of where we're going with this, is we're going to constrain lambda with it. But yeah, we're trying to study we're trying to write down the microstates of the hydrodynamics. So these are, but
These are all the states.
what?
These are not all the states.
These are all, like for the purposes of ETH, these are all the states, but the states that are actually contributing to these, the states that are actually contributing will be the ones that have the energy density appropriate to this hydrodynamic fireball.
Sorry, just if I wanted to check how many off-diagonal matrix elements are order 1 or greater,
Yeah.
then I'd want Rij to become e to the power plus s by 2 to cancel the e to the power minus s by 2.
Why? Wait, you want this or?
I want the whole off-diagonal guy to be order 1.
Oh, why do you want the whole? I don't think there are any. I think there are basically no states like that.
I was trying to check that.
Oh,
So if Rij is e to the power s by 2, then that would do it.
yeah.
And the probability for that is e to the power
I see.
minus that. Is this right?
Yeah, that's right.
So that's why there are no.
Yeah.
It's
that's
e to the
right.
power minus that.
Yes. Right.
Right.
Minus.
Yeah, e to the power. Right. And so basically part of this hypothesis is that any two eigenstates are very far from each other. Linked
Yes.
through local operators.
Exactly. That's right. That's right. Yeah.
This is true for any local operator.
For every local operator, or
Well,
every reasonable operator.
yeah. As far as we know, I mean, that's the hypothesis. It's not really known in quantum field theory whether this is always true for every local operator. In most of the checks that people have are numerical checks in small, like, spin systems. I'm going to assume that it's true of this local operator in a quantum field theory. I think it's reasonable, but we don't know.
But the basic idea is that every eigenstate differs everywhere. You take any two eigenstates and they differ everywhere.
Uh-huh.
Is
Yeah.
it,
Yes. Yes.
And so when you take a local operator, it can't fix it.
Yeah. Yeah. That's right. Yeah. So under this assumption, you can write a formula for these off-diagonal matrix elements by matching to the 2-point function, and they just are the 2-point function. So the specific formula is that this thing squared is twice the imaginary part of the retarded correlator over some density of states factors, omega pi minus omega of tj, where these are the density of states, e to the s. Okay, so the goal, so now we want to require this huge matrix. So now we have an ansatz for this matrix. The diagonal elements are given by epsilon plus p. The off-diagonal elements are this known hydrodynamic 2-point function times e to the minus s over 2 times a random matrix. Okay, so now we know the whole matrix, and now we want to demand that it has positive eigenvalues, because this is supposed to be a positive operator. And for that, maybe I won't go through the details. There's a simple well, no, it's easy enough. Okay, so positivity tells you then that E plus P, the energy density plus the pressure, is greater than the maximal eigenvalue of Tij, Rij, which was this correction to the T++ matrix. So this is basically the same as before. It's telling you that the off-diagonal, the diagonal pieces, diagonal contributions to the matrix have to be bigger than the off-diagonal pieces. And
You would sort of get it as E plus B squared is greater than this.
yeah, it happens. Yeah, exactly. And the largest eigenvalue of a random matrix you can calculate, or you can bound rather by the sum of its elements. Okay, so
You're applying it on a 2x2 block of this whole thing?
no, this is to the whole huge matrix all at once.
Okay.
Yeah, if you do it to a 2x2 block, then you don't get enough. It's not strong enough. You really have to apply it to the whole matrix.
This Tij, Rij is the matrix with the diagonals removed. Is that?
That's right. Yeah, it's the off-diagonal piece of the matrix. Yeah. Okay, so when you plug in all these formulas and ask the matrix to be positive, you get a constraint that looks like this. Epsilon plus p squared is greater than or equal to 64 pi cubed over L to the fifth, integral d omega sine squared L omega over 2 over omega squared e to the minus omega over 2t times the imaginary g r t plus plus t plus plus of omega k. This is the hydrodynamic two-point function, which depends only on the transport coefficients and is some known but sort of ugly function of momenta. Everything else in this, everything else here is known, so now you just have to do the integral. The integral is very ugly, but can be done numeric. It's just a one-dimensional integral that you can easily plot for whatever set of parameters, your transport parameters you're interested in. So this is some big, messy inequality on all these quantities we've been discussing, epsilon plus p, the cutoff, eta, zeta, and cs. The cutoff is entering here because it was the size. It's related to the size of the box that we have to use. That we have to take a box that's big enough to have nice hydrodynamic description. So that's how it's entering.
What is K is determined in terms of omega, or K is immaterial?
K is anything. Oh, sorry, here? K is anything, but here we also set K to be the cutoff in order to get the strongest bound. So the cutoff enters twice. It enters there, and it enters in K.
So the inequality should be valid even for small size box, right?
Well, the exact inequality will be true for a small size box. But we won't be able to use like ETH with these matrix elements if we take a box that's not described by hydrodynamics.
What is the capital omega?
That's the density of states, e to the s.
But is it not that, like suppose I take k goes to 0 limit, and this k goes to 0 limit, that is like a Kubo formula for the transport coefficient, say eta or something. Will that not give me some do I have to take k to be larger? I can just
Yeah, so, yeah. When I say we put at the cutoff, that means we take k to be as small as possible. Yeah.
So can you explain once more the relation between lambda and L? The relation between lambda and the size of the box.
Yeah, lambda is 1 over L.
It's 1 over L. I see. So for
Well,
large,
up to a
lambda L is
up to a factor of say 10 in order to safely be able to do hydrodynamics in your box.
You're making the box as small as you can.
Yes, you have to make exactly. You make the box as small as possible while still allowing it to be big enough for hydrodynamics.
okay.
And that's why you end up with constraints on the cutoff.
So,
The smaller you try to make this box, the stronger an inequality you'll get. Okay, so let me end with just a few comments about the conclusion here. I've lost my, here it is, eraser. Okay, so, well, I already gave you the plot. As I said, it's sort of it's really just this quantity on the right sort of ends up just being an order 1 function for generic values of the parameters. So if you just make them all generic, then you basically just end up with an inequality that looks like this, so everything else just drops out. You can calculate them, just set everything to 1. Then what you find is left over is just the energy, is just the entropy of the box. This is the energy density times the volume. So it just says that the entropy of the box has to be a biggish number. Okay, so this is really just restating for you what you mean by hydrodynamics making any sense. Although now we've just derived this in an elaborate way from the ANEC. You know, we wouldn't really expect hydrodynamics to make sense for a box that didn't have a lot of particles in it. That's essentially what this is saying for generic values of the parameters.
10 to the power 3 was 64 pi cubed.
Essentially, yeah, that's right. Yeah, that's right.
Shouldn't ANEC have even something more than this? Because maybe you're going to say that.
Well, now I'm going to take some limits. That's what I was. Okay, so so you get some non-trivial bounds. Well, I don't know if this is, maybe there's some non-trivial content here already. I don't know about this 10 to the 3, exactly where to put that. This is kind of pushing the regime of validity of hydrodynamics, but systems like the QGP are also pushing the regime of validity of hydrodynamics. They seem to be hydrodynamic in systems that are very small, where you wouldn't necessarily expect hydrodynamics to kick in. So maybe there is still bound there, but it's not clear. So to really get non-trivial bounds, you have to take some limits of your parameters. So for example, if you take the speed of sound to be small, then you get a bound that looks like this. Lambda cubed is less than s times cs squared. So this, in other words, as the speed of sound gets small, you have to have a much larger number of particles in your box for it to behave hydrodynamically. So this tells you that as the speed of sound goes to 0, the cutoff of your effective field theory must also go to 0. Okay, so this is a non-trivial constraint. You can also get constraints from other sorts of limits. There's one for large eta and zeta, which I won't write down explicitly, but because it's not very illuminating. But there are some cases, the point is just that there are some cases where you get non-trivial bounds. The last comment I want to make is just to speculate. on the connection between this and the conformal bootstrap. So in a, well, we'd like to understand what's a more universal, definitive way of getting bounds like this, and to understand what are these order 1 numbers that we can't probe, and to also be able to eliminate this assumption about eigenstate thermalization, which we don't know to be true necessarily of this operator. So how would we do that, at least in principle? Well, one possibility is to think about 4-point functions. So
I'm sorry. The speed of sound is measured in units of the speed of light, I presume. Right?
yes.
So in a non-relativistic theory, in a very massive theory, the speed of sound can be very small.
Yes.
Does this? I couldn't follow through on the. Does this say something interesting about that limit?
Well, it tells you the cutoff of hydrodynamics has to be small. But what more would you want?
Yeah. It tells you the cutoff of in that limit. Say I've got a non-relativistic gas, particles of mass n.
Yeah.
What will it tell you? The cutoff of hydrodynamics is small in units of what?
Okay. If you just have massive particles,
Yeah.
then
gas at the end.
I don't think that you get a non-trivial bound in that case. Let me try to remember why. Okay, maybe we can talk about it after. I don't quite remember what happens with the massive particle case,
Okay.
non-relativistic particles.
Okay.
Yeah. Okay, so one option for trying to study this in a more detailed quantitative way is to think about 4-point functions. At least in a conformal field theory, all of hydrodynamics is hiding somewhere in 4-point functions like this one. So, well, I can make these 2 different operators. We said hydrodynamics is a statement about TT in these high energy states, and high energy states are just created by high dimension operators. So if we could bootstrap correlation functions with 2 heavy operators and 2 stress tensors, then in principle we should be able to extract hydrodynamics and transport coefficients from that calculation. There's been a lot of progress in recent years in bootstrapping, in calculating numerically and otherwise 4-point correlation functions in conformal field theory, but it hasn't yet been at the point where you can study hydrodynamics. And the reason for that is that you need these these 2 operators to have large scaling dimension. And Bootstrap has not yet gotten to the point where you can do that. But I just wanted to mention this as a target in principle for future efforts to bootstrap 4-point correlation functions, is that maybe a really interesting quantity to try to calculate are these transport coefficients. And in principle, at least, we can calculate them just by pushing up the 4-point function bootstrap to higher and higher scaling dimensions. And then we should be able to extract transport coefficients from there. And to check things like what I described, this property of matrix elements of the ANEC operator. This is going to require new techniques, essentially, in order to get up to high dimension, because now there are a lot of operators involved. And the numerical techniques that we have now don't work or just aren't fast enough to handle problems that are this big. So it's not clear how to do it. But I think it's a good goal for the bootstrap. Okay, I'll stop there. Thank you.
Any questions? ICDS?
Hi, I have a question. Hi, can you hear me?
Yes.
Yeah. Okay, so you are using this ANEC and ETH to get some bounds on this transport coefficients. And in doing so, you have this inequality where you have to perform a omega integral, in getting this bounds. So my question is, this L box, which is coming from this x plus integral that you have, So this L box, keeping various theories in mind, do you input this L box in numerics and get the bounds on various transport coefficients and check the consistency? Is that how you let's say in case of the theories that can be tested in lab, do you give a proper L box accordingly and check get the transport coefficients bound coming from there, and whether that's consistent with lab experiments and
So the answer is that L box is here a purely theoretical trick, and that if you're comparing this to a physical system like QGP or something else that you would build in a lab, the thing you would measure is actually the equilibration time of the hydrodynamic theory. So like in QGP, and there are also say in cold atoms experiments where they measure hydrodynamic transport, the observable there is equilibration time. That sets for you the cutoff of the hydrodynamic theory. And then here, this is just done. Here, we just need to make sure that we're studying a hydrodynamic box, a box full of hydrodynamic stuff. So it's not. So it's a different. So the L box here is not a physical one. It's just for the trick of applying the ANEC. And the physical thing you would measure is that decay time.
Yeah, I have a question, Tom. See, in the beginning of your talk, you mentioned about how this ANEC condition has been arrived at in studies of gravity. But it is also true that the ANEC condition is violated. For example, recently there are these works by, Maldacena and Chi, for example, in the SYK model, and Gao-Jaffaris wall, in which the ANEC condition is actually violated in order to get a consistent dual. So you have any comments about this difference?
Yeah, so there, what's being violated there is the ANEC in curved space. Here I was always in flat.
Yes.
Here I was always in
Yes.
flat space.
Yes.
In curved space, we have to first of all, there's no derivation of any ANEC-like thing in curved space or coupled to gravity. There's a guess for what is probably true in a theory of gravity, and it's not the ANEC, but what's called the achronal ANEC, which has an additional requirement that you have to make sure that all points on your null ray that no 2 points on your null ray are time-like separated from each other. So it's known that you can violate the ANEC on null ray in curved space-time. It's known that you can violate the ANEC on null rays which have time-like separation. So a famous example is the photon orbit of Schwarzschild. So this is like a corkscrewing null ray in space-time, and the ANEC is violated on that null ray. As far as we know, it's never violated on achronal null rays, and that also is an escape in these traversable wormhole constructions that because of the left-right coupling that's necessary to make the traversable wormhole, the null ray that violates the ANEC actually has time-like separated points on it, so it doesn't violate this condition.
Any more questions at ICPS? HRI questions?
No, I think nobody had any question.
Okay. Any questions? Yeah.
This story about bootstrapping to get transport coefficient, has this been explored in D equals 2, for example?
So the question is whether this bootstrap problem has been studied in D equals 2. The answer is that the TT heavy correlation functions have certainly been studied in D equals 2. There is unfortunately, there's no interesting transport coefficient to calculate, as far as I know. Transport is sort of trivial in two-dimensional CFT. There could be. I'm not sure of that, but nobody has really studied it and found interesting transport to look at. There's no 8 over S in 2 dimensions, so I'm not sure exactly what one would try to calculate.
So is the problem with largely is because of like suppose I have all the scalars, still it is not known. Like
That's
in
right.
PT,
Yeah, I think in order to so say you want like the 100th, say this is delta equals 10 or 20 in the 3D Ising model, then as a prerequisite, I think you probably need to bootstrap all of the lower dimension operators first. And when in the numerical bootstrap, you have to form a matrix of all the low-lying operators. So far that can be done with like 4 or 6 operators, but you can't do it with 100 operators. The matrices are just too big, and the optimization never converges.
So I was wondering if, like the ANEC, you have in a relativistic field theory, do unitarity and causality also give you some similar integrated energy conditions, maybe on some Cauchy's lines, space lines?
So did you say in a non-relativistic or
No, in a relativistic theory.
Say the question again?
So the question is that do you get other integrated energy inequalities
Oh.
similar to ANEC, say on a Cauchy's lines? Or
well, the only ones I know of are the ANEC and the total energy. I don't know of other
so like the
integrated.
dominant energy condition, do you have any integrated versions of that or something?
There's no, as far as I know, there's no integrated version of the other energy conditions that's known to be true. There may be exceptions in 2 dimensions, but in higher dimensions, I'm not aware of any.
So this ETH conjecture, would it imply the following? So suppose I take n equals 4 Young's theory on a sphere. Just n equals 4 Young's theory on our form, and I can compute a 3-point function of 2 operators of dimension of order n square, and 1 small operator, and then everything you said for the matrix elements would be true of this 3-point function, right? So it would say that you take any 2 eigenoperators, any 2 operators which have definite scaling, which are primaries, maybe a definite scaling dimension, and then you compute this 3-point function. This off-diagonal term is very small. So,
Yeah.
is it, so I was wondering, is there a holographic way to? Could we check this somehow? Could
Like
this come out of an instant on
some black hole,
something.
like Hawking radiation type.
Some even for some instant some Euclidean, I don't know.
In 2 dimensions, the answer is definitely yes. But well,
I suppose the problem is putting your hands on different energy items, different operators.
yeah, it's not some obvious thing like a you might think it was just a black hole emitting a Hawking particle or something, but that doesn't really work. I'm not exactly sure what the experiment is that's supposed to tell you it's exponentially suppressed.
Right.
I'm not sure.
The upper bound on beta over S, if it exists, then presumably it should be somehow related to the chaos bound.
The upper bound?
Bound.
Why do you want it to be related to the chaos bound?
I mean, I don't know. I was just speculating. Because that is one thing that one can try to get a more fundamental handle on. Right?
You're thinking of upper bound on 8 over S or on S over eta? Okay. Well, the causality bound that I stated is an upper bound on 8 over S. That's given by the equilibration time, basically. I don't know. I mean, okay, so yeah, part of our original goal was to use the chaos bound to say something about transport, but there's a big problem with that, which is that if you try to think about this as so the chaos bound is a statement about correlation functions, like this one. And if you try to think about the regime of the 4-point function responsible for transport, versus the regime of the 4-point function responsible for chaos. These are two, the kinematics are the same, but the orderings are different. So like in order to get from the, if you want to look at this correlation function and calculate a chaos quantity, you have to go around a cut in order to get to the transport regime. So there's no obvious relationship between them. And in something with a gravity dual, it's actually the same physics that's responsible for both. It's the graviton in the bulk that's responsible both for transport and for chaos. And in that case, it is sort of the fact that you have maximal chaos and the fact that you have 1/4 pi are related to each other, because they're both coming from the graviton dynamics in the bulk. But more generally, these just seem to be totally different regimes of the 4-point function, and it's not clear how to place any relationship between them. That was we were kind of hoping, but we didn't find a way to do it in general.